Welcome everybody to the Kubernetes hands-on workshop. We're going to dig into Kubernetes and you'll get a lot of time to be able to work through things. We only have 3 hours and we definitely have a whole lot more content than that. So I hope that after this is done, that you'll continue learning about Docker and Kubernetes. It's going to be so much fun. I'm going to paste the link to the code here in chat. And so that will be the courseware that we work from. I hope that you've already had a chance to get Docker Desktop installed. Here's that website. And if you come to step 0, it will walk you through the process of getting Docker Desktop installed in each environment. For a Mac, it's really easy. You just take this icon and you drag it to there and everything just works. For Windows, it's a little bit more involved. You have to turn on virtualization in your BIOS, perhaps. Then you have to install the Windows subsystem for Linux version 2. And then finally, you can get the Docker installed. On Linux, it's actually quite a bit easier, but it's specific to the Linux install that you have. So you'll need to follow the doc specific to your Linux distribution. Once you've got Docker installed, then down here, we're going to take a look at, we'll enable Kubernetes mode. So go into settings, click on Kubernetes and click on enable Kubernetes mode. Once you click apply here, it will take a few minutes for it to download all of the images associated with Kubernetes. And so, yeah, it feels frozen, but it's actually doing quite a lot of work. Once you get the 2 lights saying that Kubernetes mode is running, it actually looks a touch different now. But you can come here in Mac, it's up here on the top toolbar, and Windows, it's down here. And you can come in here to the Docker whale, and you can see the Docker whale. Oh, it looks like Zoom is going to compete. Okay, so I've got Docker Desktop starting. Uh-oh. Engine null. Docker image list. It is still running though. Yep, it is. So I'm not sure why my Docker Desktop. Oh, that's why. I've got it running twice. There we go. So Docker is running. I've also got Kubernetes mode running, and that's perfect. The next step we'll want to do is test it all out. And so we'll do a Docker -- version. And that will show us that we're running a modern version of Docker. In this case, I'm running 20.10.10. If you're running a 1 point something, then you probably need to update. If you're running a 19 or a 20, you're probably okay. The next step is kubectl version. And this spits out 1.22.2 and 1.21.5. That's fine in this case. I don't like that Docker does -- version and Kubernetes has no dashes, but that is the way it is. Once you've got those pieces in place, then we'll want to pull these images. So I'm just going to copy this and I'm going to set it in place. And I've downloaded them previously, so it'll say, hey, you've already got the layers. But that's what we'll want to do next. So if you haven't done that, take the chance right now to get Docker installed and get these images pulled. And while we do that, let's talk a little bit about what is Docker. Now, this was step 0 here in this courseware. And so next stop is step 1, welcome to Docker. Now, wait a minute. This is a Kubernetes workshop. Why are we starting with Docker? Well, the premise of Kubernetes is, so you have a container. And the way we build containers is with Docker. Now, the interesting part is that Kubernetes is the process of running containers at scale, and Docker is the process of building those containers. Now, there are other ways to build containers. We could use BuildKit or runC. There are other ways to run containers. We could use Mirantis or we could use DCOS. But Docker for building and Kubernetes for running are pretty much the standards, which is why we'll start here. So let's talk about what is Docker. Oh, I haven't introduced myself. I'm Rob Richardson. I do a lot of Docker and Kubernetes training and consulting. So if you like this workshop and want to dig in deeper, then definitely hit me up. We'll have a lot of fun. Some of the other things that I've done, I'll head over to robrich.org and click on About Me. I'm a Cyril developer advocate. If you're struggling with your data mesh, I would love to learn from you. I'm a Microsoft MVP, a Docker captain, and a friend of Redgate. AZ GiveCamp is fun. AZ GiveCamp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver the completed software to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp, or if you'd like a GiveCamp here in Porto, or wherever you're connecting from, I would love to help you with that. Hit me up on email or Twitter, and let's get a GiveCamp in your neighborhood too. Some of the other things that I've done, I replied to a .NET Rocks podcast episode. They read my comment in the air. They sent me a mug. Woo! So there's my claim to fame, my coveted .NET Rocks mug. So let's dig in. Oh. Apologies. I did not click the waiting room correctly. So welcome if you're just joining us. If you're just joining us, welcome. The code for our content is here on GitHub. I'll paste the link to that in chat again. Nope, not that. And we are going to take a look at what is Docker. Now, we're starting with Docker because Kubernetes begins with, so you have a Docker container. Let's talk about Docker. I'm going to say docker run -p 8080 80 new nginx alpine. Now that I've done that, I'll come in here to my web browser and I will say localhost 8080, and I reach my Alpine, my nginx server. Oh, or it's still starting up. There we go. Now it's started. There we go. Now we've got our nginx server running. Now that was super easy. I'm going to hit Control C, which I think I've got my terminal set up to not allow that. So let's list the containers that we have, and I will say Docker container stop. Docker container RM. And just as easily as I was able to spin up that server, I can now take it down. And if we come back to our website, it's not, there we go. And our server is down. Now that was really cool. We're able to take our content and spin it up really easily and then spin it down really easily. When we look at Docker, we have this really elegant mechanism of creating these machines. Now, isn't Docker just like VM++? Well, it is, but it isn't. We still have that sandboxed environment. We still have a unique host name and IP address per container, but we're virtualizing the operating system as opposed to virtual machines that virtualize the hardware. With a virtual machine, we provision how much RAM, how much CPU, how much, what drives we want to attach it to, and then we install our operating system. With a container, we're using the host operating system, so we're only configuring the amount of RAM and CPU assigned to each piece. Docker is ephemeral, isomorphic, and deterministic. That means it's short-lived, unchanging, and the same every time. With a virtual machine, we'll probably start it up and we'll leave it running for a really long time. By comparison with a container, we'll start them up and spin them down really quickly. A container may only live for an hour or a day. And at that point, then we'll kill it off and spin up a new one. They're ephemeral, they're short-lived, they're isomorphic, they're unchanging. So if we want to patch a system, we don't actually run Windows Update or apt-get update inside of a container. Instead, we'll build a new container and we'll spin that one up instead. So it's a great tool chain for both dev and ops to be able to get our content running. It clearly delineates duties between dev and ops, and it's a clean communication strategy where both developers and operations can focus on getting our systems running. You know that big Word document that you have that specifies all the details about how to deploy, of which step 7 says configure configuration, and step 13 says apply the security settings. Yeah, we don't need that Word document. We now have configuration as code that specifies all the details that we need to be able to get started. So we've started in the middle, and let's back up and start kind of at the beginning. Docker. Docker is this ecosystem around container virtualization. Containers are this lightweight kernel virtualization where we're virtualizing the operating system instead of the hardware. And so Docker then is this ecosystem, this suite of command line tools that allows us to create these containers really easily. Now, namespaces, jails, CNAMEs, cgroups, all existed before Docker came. But creating these things was hard. Docker created this ecosystem to make them really easy to use. The analogy I like here is, what's the difference between XML HTTP request and AJAX? Well, from a technical perspective, nothing. But from a user standpoint, XML HTTP request is the thing that powered up Outlook's right-click menu in the 80s and in the late 90s. And AJAX is the thing that powers Facebook and Google Maps and that site that you're going to build today. So Docker didn't create containers. Docker just made it easy to use. Now, you may have seen a graph like this. I think as an industry, we're almost past this, but this kind of highlights that difference between virtualizing the operating system and virtualizing the hardware. On the left, we have virtualizing hardware. We have our typical virtual machine environment. You can see that we have lots of copies of our operating system, one for each virtual machine. On the right, we have containers. Now, we still have a Docker hypervisor here, much like our hypervisor, Xen or VMware that we have here, but we don't need a copy of the operating system. We only need the difference between the operating system here and the content that we're going to use in our container. So definitely not to scale, but we can see that we're using our hardware a lot more efficiently here. That's excellent. Containers then need to use the same operating system as the host. Linux containers run on a Linux host, and Windows containers run on a Windows Server host. What's missing?
A lot.
A lot? Well, what about GNOME and KDE? What about Red Hat and Ubuntu? Can I run a Red Hat container on an Ubuntu host? I can, because the thing that we're virtualizing is Linux. The Linux kernel underneath the containers is the thing that we're virtualizing. So if I have an Ubuntu host and a Red Hat container, that works just fine. Or a Red Hat host and an Ubuntu container, that also works just fine. Now, for the purpose of standardization, I may choose to have all Red Hat containers and all Red Hat hosts in my organization. That's fine too. Or I may choose to have Alpine-based containers that are really lightweight Linux virtual machines. Or maybe my host will run a different OS. Now we have Linux and Windows. What about Mac? Or what about Windows Desktop? Wait a minute. I just went to docker.com and I downloaded Docker Desktop for Mac or Docker Desktop for Windows. Is that a lie? Kind of. It works like this. On the left, we have our developer setup, and on the right, we have a production setup. On the right is exactly what we want to do in production. We want to run as close to the metal as we can. Now, maybe in our cloud, this host is a virtual machine instead of a physical machine, but either way, we want to get our containers running as close to the metal as we can. But in development, we might want to do something like this. I have my Mac or Windows laptop. I have my host OS. I have my hypervisor. In the case of Windows, it's Hyper-V. In the case of Mac, it's HyperKit. And then we install a Linux virtual machine. We'll install the Docker engine inside that Linux virtual machine to be able to run our Docker containers on a non-Linux operating system. Now, the cool part about this is we can put another virtual machine here in place as well and use it just like another virtualization platform. Docker Desktop does all of this for us, which is amazing. So we don't need to set up this guest OS. If you're on Windows using WSL, then WSL2 can act as this Linux host, and then the Docker engine gets installed there. That's great. In development, we can use this to run Linux containers on top of our Windows host. In production, it'll run more like this. Now, I'm on Windows, so I can right-click here, and I could say switch to Windows containers. We're not going to run on Windows containers today. We'll run on Linux containers. But if it says switch to Linux containers here, then you're going to want to take advantage of that. Switch to Linux containers, and then pull the containers that we'll work with today. So I have my Windows host, I have my hypervisor, I have my guest OS, and then I have my Docker hypervisor here that allows me to run the Linux containers. Perfect. Let's take a look at the Docker ecosystem. Now, the cool part about this map is that it is the mechanism of getting from configuration as code to running containers on the Docker hypervisor. We have a Docker file, and this Docker file is that configuration as code. The steps that we need to get from a container, from our source code to a running container. We'll take that Docker file and we'll build it into an image. When we have that image, we can choose to share that image with others using Docker Hub or another container registry. And we could pull down images from Docker Hub. Maybe we'll pull down the Redis image or the Postgres image. Whether we use a Docker file or pull our image, now we have an image that we can use to start as a container on a Docker hypervisor. In this case, I chose to run it on Docker machine. We plug in Ethernet, we plug in power, and that image becomes a container on that Docker hypervisor. A Docker file gets built as an image and run as a container. As we work through the exercises today, there's going to be a couple of places where the container isn't running correctly, so we'll change the code in our Docker file, and we will need to rebuild the image and then restart the container. We'll need to do both of those steps. Now, one Docker file produces one image that runs as one container, but I could also use a Docker compose file to reference many Docker files or many images up on Docker Hub, pull or build all those images and start them together. I might run that on Docker Swarm or even better on Kubernetes. The Docker file, that configuration as code, into an image running as a container. Any questions so far about Docker?
I don't.
The flickering blue light in the top left. I don't see the flickering blue light in the top left. Is that this blue light? Sorry about the blue light there, Joyo. Okay, installing Docker. We did that with Docker Desktop, so we'll just breeze through this process. But by the way, installing Docker on Windows Server is quite a bit more involved. Docker Desktop automatically created that Linux VM. We automatically got our command line tools. When we turned on Kubernetes, we also got the Kubernetes command line tools. That's awesome. It will proxy localhost traffic into that virtual machine that allows us to get at our containers. Let's take a look at a Docker file. Now, the Docker file is that configuration as code that we need to be able to get from our source code into our production image. Now, there's four main commands here: from, copy, run, and CMD. Now, we see that there are other commands, but those are kind of the four main ones. Our from specifies the base image that we'll build on top of. Copy copies content from our local machine into that image. In this case, we're copying it to the current folder specified by this workdir. Then we can run things from the command line. Now, each of these commands will create a layer inside of our Docker file, or inside of our Docker image. And Docker can cache each of those layers, which can be really helpful. All of these run at build time as we're taking our Docker file and turning it into an image. CMD is that final last piece that allows us to specify the command that it should run as it starts the image into a container. So if we have two CMD lines, pardon me, it won't start two processes, but rather the last one in wins. So if our if our base container happens to include a CMD and we want to override it, that's completely easy enough. We'll just specify a new CMD. From, run, copy, and CMD. And those are the processes that'll get us from the get us the configuration as code. From starts from a base image. And as we look at that base image, in this case, we were using from node. So I'll go to hub.docker.com and I'll go search for node. And here's that image that we pulled, the node official image. Now there's lots of different tags, lots of different versions of this image that we could choose to use. In this case, we just chose node, not that one, node, which by default will use this latest image. Now, latest is a little bit of a misleading name. It isn't actually the latest image, but it is the image that is pushed with the tag of latest. So we've got that one. And if we click through here, we can see here is the Docker file that they used to build that image. That's pretty cool. We can see some run commands. They've set some environment variables. It doesn't look like they're copying stuff. It looks like they're downloading stuff, but they also set a CMD, which is pretty neat. So there's our Docker file. The Docker file has all of these commands that will set up the various layers inside of our Docker image. Now that's really cool. We have this layered file system. Each line in the Docker file creates a layer, and each layer is cached on our machine. So once we have a layer that exactly matches this hash, we don't need to download it again. Now that's really cool. Let's take a look at these layers. So imagine I have my base layer that defines file 3 and file 4. In the next command, I'm going to add file 2. In the next command, I'm going to add file 1. I will delete file 3, and I will add file 4. So when my container starts up, I'll have file 1, I'll have file 2, there will be no file 3, and I'll have file 4. Now that's cool. We can build up these layers, and once I've cached this layer, I don't need to download it again. But once I've got all of these layers set up, my container just sees the full file system. Now that's really helpful because in this case, maybe I didn't want to add file 3 and file 4 here in this base layer because I deleted it and changed it here. I could use my layers much more efficiently by specifying the content that I wanted to add or remove at each step. Because we have these various layers and because downloading the layer automatically gets the content into place, we can think of this much like a Git history. If I've downloaded these layers already, I don't need to download them again if this image and if this image use that same base layer. That's cool. So we might have some really heavy base layers, especially when we're working with Windows containers, but the content that we'll download as we iterate our application is probably only these few layers at the top. We don't need to worry about that. Now, if our base layer does have bug fixes or updates, then yes, we will need to download the entire stack again. Our layered file system. So here's the code in our Docker file. Here's the code in their Docker file. And we can see at the very top that they depend on this Docker file. So we could look at that Docker file and pull up the content there. Here's that image. And looking at the details, what is the image that it's looking for? Bullseye. Here's the Docker file that built that image. And we can see the content. It's pulling in some G and GCC content, and it depends from this layer, and it depends from that layer. And eventually we'll get down to the bottom where it depends on Scratch, meaning no content. So turtles all the way down. I really like this analogy of being able to look at each of these layers inside of the Docker file. As we start up with a container, we end up with a new read-write layer over the top of that. Now, this read-write layer is specific to this container. So if we launch 2 instances of the container, they will have separate read-write layers because it turns out that file systems don't really, or systems don't usually like running on read-only file systems. Now, if we can get to that point, that's ideal. but they may want a spot to write temp files or log files. And that's what gets into this read-write layer. So the cool part is if your container gets popped, if it gets compromised, and they start trying to delete or change content down here, they're not actually changing content. They're writing new files into the read-write layer. Well, since these are ephemeral, isomorphic, and deterministic, if a container does get compromised, pop it off the stack, pull new content into place, and we can continue on. That's perfect. We'll talk a little bit about volumes here, but we're not going to dig into it too much today because our goal is to get from Docker straight into Kubernetes. But we can think of that as kind of like a little puzzle piece that we yank out of the container and put somewhere else. We will symlink a particular folder into place in this container. Now, the command to do that will say Docker run, and we'll pass in some parameters, passing in the host folder, the destination folder to be able to map in that container. We saw the Docker run command a little bit previously. So we've kind of gone through that process. A Docker file goes to an image starts as a container. To build that, we'll say Docker build, and we'll do a dot. That dot specifies the current folder that we'll use as our base folder for building. We could also do a Docker build, but from a different folder. It's a lot easier just to say, Docker build dot. Then we'll say Docker image list, and we can choose to remove an image by saying Docker image rm. I've specified a lot of these commands, not so much so that we can go through them today, but so that you can use these as reference. When we get to the point where we're going to run, we will specify an image name, and we'll say Docker run that image name. Then we can do a Docker container list and take a look at the containers, stop and remove a container. So let's do that. I have here here in step 2, we have this hello Docker folder. I'll actually do it here from the GitHub repository. We have this hello Docker process. And I love that I have a done folder and a start folder. You can start with the start folder, but you can also kind of cheat and look at the done folder. So our task is to get to here. If you haven't yet, clone this repository so that you can start inside this hello Docker folder, switch to Linux containers, and then we'll start out building our content. Let's do that together, and then I'll let you do it on your own as well. So I'm going to open this folder inside of VS Code. Let's open it here. Show more options, open with code. And our first task is to get a program that we want to build. So let's create a new file. Server.js. I think that's what I called it. Did I call it server or did I call it index? Yep, I called it server. Okay, then we'll head off to node.js.org. And we will come to about. And here is the content that is a node server. Okay, let's set that here inside. Oh, did I not create a file? There we go. We'll set that inside of server.js. Now, I do need to remove the host name here because otherwise it will only listen on localhost on the loopback adapter. And so I'll remove that. And if we want to remove this as well, we definitely can, but that isn't necessary. Now that we have our content that we want to run, next we'll create a Docker file. Docker file. Now, it's important that this be named Dockerfile and not dockerfile.txt. So if you accidentally named it dockerfile.txt, easy enough. Switch it out and just say Dockerfile. I have the VS Code Docker extension, so it's showing me the whale. I kind of like that. Now, next up, we want to craft this Docker file. And here in the instructions, it will show us the steps that we need to do. So we'll write this from node Alpine. We're using the Alpine version because it's a little bit Alpine, a little bit lighter weight. Then we will copy all of our content from the current directory where we run the Docker build command into the current directory where we're running our container. And let's set that current directory, workdir/src. Now that we've got our content copied into place, we can run some more commands. Let's expose port 3000. That gives some metadata for expose 3000 for Docker to know what port it needs to run on. And then we will give it our CMD command, the command that we want it to start up. Now we could definitely say node server, and that would work, but it starts to do things like shell-c. And so let's actually do this array of quoted arguments instead. And that will ensure that it runs exactly what we want it to. Okay, now we've got a Docker file. Let's come into this folder and we will say Docker build. What was the name that I gave it? I'll tag it as hello node 0.1. And then what is the folder that I want to build from? That's that final dot. I want to build from the current folder. Now it's going to go through the process of looking through each of the lines in my Docker file and running those to build this new image. Now that we've got this new image, hello node v0.1, Docker image list, we can see there's the image that we just built. Hello node. Now let's run it. Docker run hello node 0.1. Now we don't need a dot. We're not talking about what folder we're building from. We're just going to run here, but we are going to give it some additional parameters. We are going to say, I would like to map port 3000 from my local machine through the Docker switch to port 3000 inside the container. Now that I've run that, then it will show me all of the console output here from that container. Now, oh, node not found. That's interesting. Not there from node Alpine. That is really weird. No, oh, I bet I missed a quote. I missed a comma. Now I did try and run it. It failed to start. I can say Docker container list, and I'll push in -- all, so it'll show me both running and stop containers. And there's that container that didn't work. Okay, so I fixed my code. Docker build -t hello node 0.1. And I will rebuild this. Now, the cool part is that a lot of this is cached. It didn't need to rebuild the content because it was already cached. It only needed to fix that one line at the end. Now let's do that Docker run command again, and we'll start up our server. So here comes the console output. We'll see that listening on localhost 3000. And so we'll come to here and we'll come to localhost 3000. And up starts our server. Now, when I'm done, I can hit Control-C. I've got my terminal broken a little bit. So I'm going to say Docker container list. And now let's stop that container. Here's that container, Docker container rm-f. I'm going to stop it and remove it at the same time. And now that container is coming down. There's that hash of it. Now, I could use this name, or I could use any portion of this name that makes it unique, this container ID. I could also use this name. It happened to give me the boring Elgamal name, and that's kind of interesting. And so it's usually easier to say this as I'm talking to people, but this image ID is often easier to type. That started it up and actually shut it down as well. So the cool part is we were able to spin up and we were able to build an image and start it as a container running on this Docker hypervisor. It automatically started the process, assigned a virtual IP, and added the traffic to the container. And that is really cool. We can dig through some other, so I want to run 2 servers. I just run Docker run again. That's pretty cool. A good rule of thumb is 1 container is 1 process. And that's really a focus that we want to do going forward. If you want to run 2 processes, you probably want to run 2 different containers. One of the things that some IT departments will say is, but I really need my corporate agent running inside of your container. No, you don't. You need your corporate agent running inside the cluster. It should run as a separate container. One container is one process. Now that's really interesting because Docker will actually monitor that process. And if that process terminates, like in our case where we tried to run the command incorrectly, then Docker will notice that that process has crashed and crash the container as well. So we've got that. As we did this, we mapped port 3000 from our local machine, the WAN side of the Docker switch, into the LAN side pointing at that particular container. And that's pretty cool, is that we can map from our local machine through the Docker switch into one of these containers. Like we would set up any web server, we can choose to map ports differently. So maybe I'm going to accept port 3001 into this container, port 3002 into this container, port 3003 into port 80 of this container. And so we can just map those however we need to across the Docker switch. So I've got these three WAN ports, I've got these three LAN IPs, and Docker will keep track of that to be able to forward the content in the correct spot. So I specified this local port, and I also specified the port that my container is listening on, and I can just specify an image name, optionally a version number, and it will map from port 80 on my local machine to port 5000 inside of the container. That's cool. So we could also map data volumes. We won't dig into that too much today, but that is interesting. We could also specify commands that we want to run to override that CMD command. And so that's pretty interesting. Docker logs. Ooh, Docker logs. Docker container list. Let's take a look at this one container that we had, and let's do Docker logs on that container. Did we get any console output before it died? Yes, there's the console output that is really helpful in being able to identify why this container had a problem. If your container doesn't start up correctly, Docker logs might be the perfect solution. A Docker file gets built into an image, gets run as a container on the Docker hypervisor. That's cool. Our next step is to take a look here at this Hello Docker. Now, this Hello Docker is a rather simple one, but the next part of that is chapter 3, a multi-stage build. And a multi-stage build will start building 2 different images at the same time. And finally, we'll get to a bigger site, 2, 3, and 4, a bigger site where we have 2 different microservices, a front end and a back end, where we can work with them together. So that's our task, is to start in with chapters 2, 3, and 4. Any questions before we begin? Great, let's dig in. I'll come back in about an hour and let's take a look at the things that we've got. If you need me, if you get stuck in anything, then let's definitely talk through the concerns that you have and dig into all the pieces. When we come back, after an hour probably won't be enough to be able to do all 3 of these, but then we'll come into Kubernetes and we'll definitely dig into a whole lot more of Kubernetes pieces. Oh, what is the current time? My clock here probably doesn't help you at all.
It's 20 to 3.
Here it's 2:40 p.m. at the moment.
Maybe you can say in half an hour, 2 hours, hour and a half, hour 15 minutes.
Oh, good call.
somebody looks at the message, they don't know when it was written.
Word wrap. Thank you for the time there in comments.
Yeah, so basically back in 1 hour, more or less.
Yes, back in 1 hour. Please work on chapters 2, 3, and 4.
Isn't 2 what we just did?
Great question. Will the recording be made available? I believe so, but I'm not positive. Do we have some comments from the techs watching? that server. How's it look so far? Did anyone get stuck trying to debug a container that isn't starting correctly? One of the things that you'll see here in chapter 2 is a bunch of steps down here about debugging a failed container. So if that's what you're struggling with, then you might find a lot of success here. Just another minute. How did you like Docker? How do you like Docker files, starting and running containers and taking a look at building images?
Love it.
Very nice. And easy.
Yeah, it is. It's quite easy once you get into it. This doesn't work quite as well on the remote side, but how many people have Node installed? And how many people were able to run Node as part of this exercise? That's part of the beauty of containers, is that we can run content that we don't have installed. That's pretty cool.
For me, it's cool to run .NET.
Yeah.
It's the one thing
You
that I
don't have .NET installed, but you're able to
No.
run .NET?
Yeah, that is cool.
Yeah. So if I'm doing something weird, like I need to go build up a Ruby thing, or I've got a Python thing, or maybe I have a Go thing, and I don't want to install all of the pieces of that development environment, I just do it in a container instead. Or I want to run that tool, or I want to install Redis or Postgres, and I don't want to have the engine kicking around on my machine. Just Docker pull the container and start it up.
Yeah, to set up a development environment for the whole team that's consistent across everyone. I think that's also cool.
Yes, a consistent development environment is really amazing here too. So let's dig into what is Kubernetes. Now, the cool part about this exploration is we're going to take the containers that we built in the Docker side, and we're going to run them inside of Kubernetes. Kubernetes begins with, so you have a container. And the cool part there is that then, given that container that we built, we run it at scale inside of Kubernetes. Docker is about building and running containers. Kubernetes is running containers at scale in production. Google started by building Kubernetes, but they ended up donating it to the open source community, which is amazing. We now have the Cloud Native Foundation, CNCF, that runs Kubernetes along with a lot of container-based systems. Kubernetes is an orchestration engine. And when we look at orchestration engines, an orchestration engine is something that we can pool a bunch of machines together, and we can give instructions to this orchestration engine. Like, I'd like you to run 3 copies of my web server. Now, the cool part is the orchestration engine decides which machine needs to run this content. We don't need to say, hey, can you run this one over there and this one over here? We just say, I want 3 copies of my web server running. And by the way, can you keep them across availability zones? And Kubernetes will just make it happen. So I specify what I want. I don't specify how I get there. I just specify the desired state. Now in Windows, there's desired state configuration, and that is completely different, but it kind of works on the same principle. I give it the end state, and I tell the machine to go figure out what we need to do. So that pool of machines collected together, we can call that the cluster. So we'll have a Kubernetes cluster, or we might have an ELK cluster or a database cluster. That same mechanism. Given a pool of machines, we tell the orchestration engine what our desired state is, and it makes it happen together with all the other requests. Now, if a container goes down, or if a container is unhealthy, or maybe if a virtual machine or a physical machine is unhealthy, then Kubernetes can automatically compensate for that and make the necessary adjustments. Now, we have lots of different orchestration engines to choose from. Kubernetes, DCOS or Mesosphere, Docker Swarm, Azure Service Fabric, Amazon Cluster Service, Fargate. There's lots of different orchestration engines that we can choose from. Now, ultimately, I don't want to inform your opinion. I know that your organization may have different options than mine. And so you can probably walk into your IT shop and say Kubernetes and Mesosphere, and they'll be able to tell you a lot about why they chose the particular orchestration engine that they chose. And I agree, that's the correct one for you. All of these orchestration engines have that same principle. I have a pool of machines that I'll call a cluster. I give it instructions, and it makes those things happen. Now, in this case, we're going to choose Kubernetes because that's the nature of this workshop. Kubernetes is kind of one of the weirder orchestration engines, but it is kind of the one that is the most popular. So if you don't have an opinion, Kubernetes is a good place to start. Now, Kubernetes being one of the weird ones, the people who administer Kubernetes are probably not the people who run Kubernetes. So we're going to do the developer side of using Kubernetes, not so much the instantiation and administration of the Kubernetes cluster. So Kubernetes begins with, so you have a container. Now, it can either be a Docker container, or are there really any other kind of containers anymore? Kubernetes natively supports Rocket containers, which is pretty neat. And more specifically, it supports OCI containers, Open Container Initiative. If it lives up to the Open Container Initiative standard, then it is a container that runs on Kubernetes. Now, there was a big thing not too long ago about Kubernetes dropping support for Docker. Yeah, Kubernetes has embedded in it a shim that allows it to run Docker commands. Now, this shim was always meant to be temporary, but there really wasn't a good way to be able to execute Docker containers without it. But what is Docker? Docker is this build system, the run system, all of these pieces associated with Docker, and Kubernetes was just using one small piece of it. Since then, since Kubernetes embedded this Docker shim in place, the Kubernetes ecosystem has grown a lot, the Docker ecosystem as well. And we now have the Open Container Initiative and much lighter weight runtimes. So we could use Containerd, or we could use Run C, and that would allow us to run these OCI compliant images. What Kubernetes deprecated was it shelling out to calling Docker commands, not its support for Docker built OCI compliant images. Kubernetes still runs with, so you have an image, and Docker is a great place to build those images. And Kubernetes is a great place to run those images. There are definitely more build tools than just Docker, and there are definitely more runtime tools than just Kubernetes, but they work really well together. We talked about Docker, so we'll breeze through this. If I'm doing this talk, getting started with Kubernetes without Docker, then I go through these pieces, ephemeral, isomorphic, and deterministic. Let's stop for a second here and talk about this part. Now, we build containers with Docker, and we run them with Kubernetes, and we have this really elegant DevOps story. Inside the container, we can think as a developer of, well, as a machine. Let's arrange the pieces inside the container here. We'll set some content out on the table there. We can hang up the curtains. We can put this configuration file in exactly that folder. And as a developer, we can arrange this machine. And then once we close the doors on that container, we can ship that container off in a very standard way. As an operations person, I can take that container and I can treat it like a process. Plug in Ethernet, plug in power, I can control how much RAM and CPU it uses, and I can restart it really easily, much like a process. As a developer, we can think of containers as machines. As operations, we can think of containers as a process. And yeah, we're both right. Even more so, we're using one tool chain to be able to accomplish this, which is really cool. We don't have that Word document explaining the DevOps process and the steps to deploy, of which step one is throw away the Word document. We can now get these containers exactly built the way we want and be able to run them at scale. So we looked at the Docker ecosystem previously. We got to play with creating Docker files. Oh, I am unable to, oh, there we go. We got to see the Docker ecosystem previously, and we got to see how we could take our Docker file and put in the necessary steps to be able to build up an image. We saw how we could take that image and we could run it on a Docker hypervisor. Now, as we move from Docker into Kubernetes, are we going to need to throw away all this knowledge? Well, Docker is still the best development time tool, so we'll be able to use it there. But when we get to running content at scale in Kubernetes, we'll kind of split this image in half. The process of getting from a Docker file to an image is definitely best done with Docker. And so we'll still use Docker there. But the process of being able to take that Docker compose file to specify many images, being able to run them on a Docker machine, we'll replace that with Kubernetes bits. Now, these Kubernetes bits are great at being able to run these containers at scale. I say to Kubernetes, hey, I would like you to start up 3 instances of my web server. I'd like you to make them publicly exposed, or I'd like you to be able to load balance across them. I'd like to have them available in this DNS range. Kubernetes can do all of those pieces in a really elegant way. It's meant to be able to run containers at scale. So, did we waste our time learning the Docker pieces? No, the Docker pieces are definitely going to be great for development time. A Docker compose file is the perfect way to set up a developer environment. A Kubernetes file is a great way to be able to run it at runtime. So we're going to keep the Docker build, the Docker registry, Docker push. Those will maintain in our Docker mechanism. And we're going to replace Docker compose and Docker swarm with Kubernetes pieces when we run in production at scale. As we look at Kubernetes, there's kind of 3 main pieces. There's kubectl, the command line interface. There's the control plane nodes, and then there's worker nodes. Nodes being machines. Now, every Kubernetes startup has a picture that looks not that unlike this, and they point to the picture and they say, see, I explained it to you. I look at this picture and I'm like, okay, I don't quite get what's going on here. So let's talk through this picture. Now, this is probably the first and last time you're going to want to look at Kubernetes at this realm, but let's take a look. Now, we looked at kubectl, the developer command line. We looked at the control plane, and we looked at worker nodes. Those are kind of the main pieces, but now let's dig in another layer deeper than that. A developer is going to use kubectl to be able to connect to the API server. The API server is running inside the control plane and accepts requests from various places. The API server will then delegate that content to the controller manager, which will probably save it inside etcd. Actually, the API server is going to save it into etcd. Now, the controller manager is probably polling against the API server or subscribe to events inside etcd. So when a user makes a change inside etcd, the controller manager will wake up and probably tell the scheduler to make some content happen. Now, the scheduler is going to pick one of the worker nodes. In this case, let's say it picks this one on the left. And so that's the one that's going to run the content. The scheduler is going to reach out to the kubelet and tell the kubelet to launch a pod. Now, a pod is a wrapper around our container, and it is a network boundary and a security boundary that kind of wraps the container and maybe other container details. The kubelet's going to start that pod, and then CAdvisor can watch the pods in our cluster and report back through the API server into etcd about the health of our containers. Now, as users, we'll come into the system, we'll get routed through a load balancer, and we'll land on the kube proxy. Kube proxy knows which pods are supported for which services, and so we can get routed to the correct container in the correct pod. Now, the cool part about this is that we have lots of different microservices accomplishing interesting tasks. The bummer part about it is, yeah, that mayhem of connecting all the microservices, That's not really important to us being able to launch our content in Kubernetes. But here's the punchline to that diagram. Kubernetes gets microservices because Kubernetes is microservices. Each of these components here in this diagram, controller manager, scheduler, kubelet, cAdvisor, kubeproxy, and there are others, we can choose to replace with components that we would like to implement instead. Now, we don't often do that, but these are all the microservices that help Kubernetes accomplish the task that it needs to. And because Kubernetes gets microservices, Kubernetes is great at being able to run our microservices too. Any questions on the Kubernetes diagram?
I have one. What is a good, is there a good ratio between nodes and pods? Should it be 1 to 1, 1 to 10, 1 to 100? What's the rule there?
Good question. Is there a relationship between nodes and pods? It depends a whole lot on the content that you're running inside of your pod. Now, if you have a really heavy Tomcat or monolith inside of a pod, then you may not be able to get very many on a particular node. But if you have really small microservices, you may be able to get a whole lot more. So is there a rule of thumb, like, 10 pods per worker node? There really isn't. It's about understanding how full your worker nodes are and then adding worker nodes as you need extra space. Great question, though.
Okay, so I guess you always start with 2 for redundancy, then you start adding pods, and when you see that they're getting full, you add more worker nodes. Would that be an appropriate workflow?
Exactly. You'll probably want to start with 3, just in case you're upgrading one when there's a hardware failure. But yes, you'll start with 3 worker nodes. You'll put enough pods on it until the worker nodes say, hey, I'm full. And then you'll add more worker nodes from there.
Okay, that's great. Thank you.
Great question. Thank you. I can't hear you very well. Can you say it again? Okay, let's dig in. So Kubernetes gets microservices. Our first step is installing Kubernetes. And step 1 is don't. Installing Kubernetes is hard. So let's find a way to avoid doing so. Now, the cool part is in both public and private clouds, there's usually a push button for doing this. Inside of Azure, we have Azure Kubernetes Service. Inside of Amazon, we have Amazon Elastic Kubernetes Service. Inside of Google, we have Google Kubernetes Engine. AKS, EKS, GKE, you can probably get to a button push where you just say, I want one of those, please provision it for me. On private clouds like Mesosphere, OpenStack, Cloud Foundry, and there's a bunch more if you click through this link, grab the slides from robrich.org straight in the content that we're looking at, and you can find a great way to be able to provision Kubernetes clusters in a really elegant way. Wait a minute, Mesosphere. Wasn't that one of the orchestration engines that we looked at earlier? Yeah, Mesosphere has decided that Kubernetes has become popular enough that though they have their own orchestration engine, they will also support Kubernetes. That's pretty cool. So if you're on a public or private cloud, push the Launch a Kubernetes Cluster button. That'll be a lot easier. For a local development cluster, Docker Desktop is the one that we're using today, but you could also use minikube across Mac, Windows, and Linux. And that's a great way to be able to spin up a virtual machine on demand. What's really cool is I have a demo of Istio and Linkerd, and so I'll have different minikube clusters so that I can switch between these various environments to accomplish the tasks that I need. MicroKS and K3S are also really good ways of spinning up Kubernetes clusters. In this case, they assume that they're running on Linux. So you might need to spin up a VM before you hand it to it. Or if you're on a Raspberry Pi, K3S might be perfect at being able to spin up a really lightweight Kubernetes cluster. The beauty of K3S is that it assumes all of the defaults and removes all of the content that isn't the defaults, making it a lot lighter weight runtime. That's pretty cool. So in Docker Desktop, we just went in here to the whale and we went into settings and we just turned on Kubernetes mode. Oh, I've already got it up. Very nice. We just went into our settings and we went into Kubernetes mode and we just turned it on. That is so easy. That is cool. Now, I did mention that step one is don't, but it's not that hard. It's a lot easier if you do it other ways. If you really want to dig into installing Kubernetes, the tool that you'll want to look for is kubeatom. And here's a link to the docs to be able to get it set up. It isn't that painful, but as I said, the people who administer Kubernetes and the people who use Kubernetes are usually different. So if you're a developer approaching a Kubernetes cluster, the process of setting up all of the nodes and joining them into the cluster, that's probably something you don't want to take on. But if you really do, kubeatom is the Google term to search for to accomplish this task. So let's take a look at the elements inside of Kubernetes. Now, Kubernetes has a lot of different elements, resource definitions, and we're going to just look at a few. Pod, deployment, and service are the ones that will pop open today, but there are a lot more. There's ingress, replica set, stateful set, domain set, that's not quite right. Job, cron job, secret, persistent volume claim, config map. There's a lot of different types of resources to be able to accomplish various things inside of Kubernetes. We're going to stick with pods, deployments, and services today, just because those are the easiest ones to get started with and help us be productive. But as you need more stateful resources, as you need to link to external resources, then some of these other tools might be helpful. A pod is that wrapper around the container that allows us to do our work. Now, specifying one pod is interesting, but that only launches a single container. Now, really what we want to hand to Kubernetes is, hey, can you keep 3 copies of my service running? And that's where we'll specify a deployment. A deployment gives us a pod template where we can say, hey, Kubernetes, when you spin up a pod, do it like this. Now, we're going to specifically spin up a pod so that we can take a look at it, but then we'll quickly move away from spinning up pods and focus instead on spinning up deployments. Hey, Kubernetes, here's the template, and I want you to put this many of them in place, and that'll be great. A service then is the load balancer over top of all of the pods. So we'll tell the service, hey, the deployment spun up 3 copies of my web server. Would you please expose them as one DNS name internally into my cluster? Now, it is possible to expose a service publicly, but probably if we want to expose a service publicly, we'll do so with an ingress. An ingress is a great way to map DNS host names into IP addresses. Now, ingress support is not great for local environments. At one point, it wasn't supported on Docker Desktop at all. In Minikube, it's supported, but with some hacks. And so we're just going to focus on service and deployments for now. Service is the load balancer, and deployments focus on spinning up copies of pods. So we've got our user. Our user will hit an ingress. An ingress will go to a service, which is that load balancer across all of the pods, and we'll have a deployment that will specify the contents of these pods. Inside each pod is a container, and that container is the process that we built with Docker. Any questions there? Great, so let's dig in. Now, as we're looking at these elements, we will use the Kubernetes routing engine to be able to create our content. So let's imagine that we have this container that is running on port 3000, and we want to get from example.com into that container. So we'll hit example.com, our DNS will route us to ingress, and that will come in at example.com. That's our host specified in our ingress, and that will listen on port 80 and 443. Now the ingress is going to map that out to a service on port 3000. Pardon me. And now the service is going to listen on port 3000 and maybe also a node port of 32123. And then it will match that service, load balance across all the pods, and it's going to specify that out to port 3000. My pod defines that my container port is 3000, and so I'm able to map my way there. User goes to port 80, ingress maps it out to 3000, the service forwards it on to 3000 into the container. Now, it's possible for us to specify different ports here, or to have mismatches between ports, in which case, yeah, our traffic will not route correctly. Let's take a look at, go ahead.
In the last slides, there's 2 ports there, the port 3000 and the node port. What are those 2 ports? What are the differences?
Good question. What's the node port here? Let's set that aside for a little bit until we dig into the YAML associated with this service, but that is a great question. Yeah, that node port can bite us.
Okay.
So let's do that. Let's dig into some YAML associated with each of these pieces. Now, each element in Kubernetes is going to have these 4 sections inside their YAML file. They may have more, but they just have these 4 pieces: API version, kind, metadata, and spec. Now, API version and kind will specify, for example, the namespace and class name of this particular element. So I might have an API version of v1 and a kind of pod, or I may have an API version of something.kubernetes.io/v1 and a kind of ingress. That's just the namespace and class name to be able to get at that particular thing. I also have metadata where I might specify the name of this thing, maybe labels that are not that different than hardware tags. And then finally, I'll have the details associated with this particular piece of Kubernetes content. Now, these could be in JSON files, but in general, we do this in YAML. So we're going to do it in YAML today. Here's an example pod. And here we have the API version and kind. So the namespace of v1, the class name of pod. We have some metadata associated with this pod that says, hey, I'm named Nginx. And then labels that specify just hardware tags. Now we could specify the department name or the product name or product version. In this case, we just said, hey, my app is Nginx. Now here in the spec section, we have a list of containers. Now, in this case, we only have 1 container, and that's a good rule of thumb. When you get to the part about learning about sidecar containers, then it may make sense to have more than 1. But for now, in the same way that 1 process for 1 container, we'll have 1 container for 1 pod. The pod is the unit of scale in Kubernetes, and it's also the spot where it manages it. So if we had more than 1 containers and 1 container was healthy, but the other one wasn't, we'd kind of be stuck. If we want to run multiple containers, we would have them each in their own pods. So we have this container, and here's the name of Nginx. We have that image that we pulled out of Docker Hub, and we specify the ports that we're listening on. So I can take this content and let's come here inside of Docker, inside of VS Code, and we'll spin up a new file, and we'll say, here is our content. Now, in this case, I'm going to say Alpine version, so I'm not bound to that particular version, but I'm going to save this file as pod.yaml. And I forget what folder I'm in. Let me make sure I'm in the right folder.
I think there's a typo in Alpine.
There's a typo in where?
In Alpine.
Yes, thank you. I would have spent a very long time trying to find that. Okay, so here's our pod YAML file. I'm going to say kubectl apply-f pod.yaml. Now this will launch my container inside my cluster. In the same way that we said Docker container list, we can say kubectl get all or get pods. Now here's that pod. There's the pod that I've got running. In the same way that we can say Docker logs, we can say kubectl logs, and we'll say pod /nginx, and we can get the console output for this pod. If we say kubectl describe pods nginx, we can see the details about the pod that we built. Now we get more details here than we had specified in the YAML file. All of the defaults that we didn't specify, it applied into place. But we say, here's our labels, app nginx. We can see the container that it pulled from Docker Hub. We can see the port, it's listening on port 80, and it's running. Here's some events about that container. And all of that is working great. But if we were to now go to localhost port 80, it would not work at all. Now that's fine. We haven't set up the service to route traffic into our pod. So our pod is just, well, it's just running. It is running nicely. And, Kubernetes tells us that, hey, that's successfully assigned and we've got ports listening and all of that is great, but we're not listening on the host at all. Okay, kubectl delete. I'm going to pass in that pod file again and kubectl get all. And now I don't have that pod running anymore. Well, as soon as it stops, there we go. Yep, that pod is done. Now, what is this service? This is that Kubernetes API service. So if you were to kill this off, it would start back up again in a few minutes, which is perfect because I couldn't communicate with Kubernetes without that service in place. Okay, so we were able to quickly launch a pod. That's really cool. Now, we've specified a name for this pod. So if we were to try and launch this pod twice, it would go, hey, wait a minute, I already have a pod for that name. I can't launch a second one. So we probably don't want to specify a name when we step back and create templates. The pod is a unit of scale inside of Kubernetes. It specifies the container details that we need. Optionally, we can specify sidecar containers, and it specifies the Docker image and port, much like the Docker compose file did. That's pretty cool. Now, we don't have build details. Kubernetes doesn't build. Kubernetes just runs. So we don't have things like the Docker file reference and the build context. Next, let's take a look at a deployment. The deployment specifies that desired state. I want 3 pods that kind of look like this. It can also specify scaling details and restart details and other details about the quantity of pods. So here's a deployment that we might want to look at. Let's set this inside VS Code. New file deployment. Deployment.yaml, and I'll switch this to be Alpine. Thanks for helping me spell that correctly. And now we have a deployment. Here's the API version and kind, so the namespace and class name of deployments. We have a metadata section that lists its name. In this case, it's Nginx deployment. We have some hardware labels as well. We could also list other things like project, startup, company, myco, app version, v1.0. We can specify other hardware labels that we need to. Then here in the spec section, how many count do we want? In this case, we want 3. And then we have a template section. We're going to skip over selector for now. Here in the template section, this looks an awful lot like a pod definition. So let's move it to the side here. And we can see how we've got the metadata for the pod where it lists the name and the labels. That's great. We've got the spec. Here's that spec where we list the containers, the container name and the ports. Now, why is it squiggly? It's squiggly because a good rule of thumb is to specify resource details, and I hadn't yet. Okay, so now we have our deployment, and this deployment says, when you spin up a new pod, I would like you to use this recipe, and I would like you to do it 3 times. Okay, so let's come in here and let's say kubectl apply-f deployment.yaml. And the cool part about apply is it is actually a create or update. It's an upsert command. So if I come in here and I say, well, yeah, but now I only want 2, then I can kubectl apply that again, and it will just change my deployment to make it do what it needs to do. In this case, it was configured where previously it was created. Kubectl get all, and I can see I now have 3 pods running. 1 is on its way down, and the other 2 are doing just fine. Now, each of those is running. I can do a kubectl logs for each one of these pods, and it will show me the startup details. I could also say kubectl logs for the deployment. Nginx deployment. And that will show the logs for all the pods. That's pretty cool. Or I guess in this case, it only found 1. Kubectl. So I'm going to switch this now from 2 to 1. And kubectl apply-f deployment. And now we'll only have 1 pod running for this content. Now we have our deployment that wraps all of the pods and specifies how many of them. And then we also have this replica set, which is kind of an artifact of how Kubernetes was built. Deployments actually wrap replica sets, and replica sets specify the number of pods. Deployments specify version details. But for the most part, we can pretty much ignore replica sets. The only thing I do look at for replica sets is making sure the desired and the ready are the same. But I also get that from the deployment right here. Okay, so we have deployments, and deployments specify in particular the amount of pods that we want to do. It can also specify scaling details, the number that we want to scale by, the number that we always want running if we're doing a deployment that might kill off old ones and create new ones. The way it'll do it is it'll create all the new ones and then start killing off the old ones. Or based on the scale factor, we could create 1 new one, kill off 1 old one, and keep running through our cluster that way. Deployments. Next up, let's take a look at services. Now, services are that piece that load balance across all of our pods. Now, in this case, we only have 1 pod running, so it will map inbound traffic coming into the service and expose that to and route that to the pods. Here's the details associated with our service. So let's pop this open inside of VS Code. I will save this as service.yaml. And in this case, we have that same mechanism, API version and kind, v1 and service. We have our metadata. It names this Nginx service, gives it some hardware labels. And we specify the details that we want to route to. In this case, we want to accept traffic on port 80. And because we didn't specify our container port or destination port, because we didn't specify the container port, it will actually use this port as well. Now, in this case, we chose to specify to route TCP traffic. So let's do that. Kubectl apply-f service. And now that we have our service, we can now start routing traffic into place. Now let's talk about service types. By default, when Kubernetes first came out, it had a service type of cluster IP. Now this means that there is one IP across all of the nodes that is listening for traffic for this service. Now, it starts out by having a port and a target port. So in this case, it will accept traffic on port 80 and route it to all the containers on port 8000. Now, both of these are required, but if you don't specify the target port, it will use the port instead. Building on top of cluster IP is node port. Now, node port specifies one IP address per worker node. So no longer do I have to go out across the control plane and maybe back to my own worker node. I can just specify content on my own worker node to be able to get at the content. So this service is of type node port. It has the target port and port because it's built on top of cluster IP, and it now also has this node port. Now it's going to be somewhere in the range of 30,000 to 32,999. And in this case, it gets randomly assigned unless I specifically specify it. Now it does need to be in that 30,000 range. I think it's actually 31,000 to 32,999. But that node port is that port that other services can connect to. And by default, this port is exposed publicly outside the cluster. Now, if we put a firewall rule around our cluster that says we just won't accept traffic on ports above 30,000, then the fact that it's exposed publicly is likely less necessary to us. It just happens to be exposed publicly as well. But it's kind of nice to be able to route traffic just to my particular VM without having to route all the way through my cluster to get back at it. Built on top of node port is type load balancer. Now, the cool thing about type load balancer is that Kubernetes will provision a cloud resource for us. And so if we're running on Azure, it'll spin up an Azure load balancer. If we're running on Amazon, it'll spin up an Amazon load balancer. And we can specify now the load balancer IP, or we can get that automatically assigned. Now, it has the target port, it has the port, and it also has the node port, which, by the way, that's an invalid port. It needs to be in the 30,000 range. And so the load balancer has these things. Well, probably when I got to node port, I didn't really care about port. I was kind of more focused on node port instead. And when I get to load balancer, I probably don't care about node port anymore. I just want to focus on the port that's exposed publicly to my load balancer. But because these services are kind of built on top of each other, then we'll get these port and node port kind of carrying along with us. So in this case, our service was of type node port. We specified the port. We didn't specify the target port. But if we had, it would be, port 80 because it matches. And because we specified the type is node port, but didn't specify that, let's go look at what port we got assigned. 32,295. Okay. Now that's the port that is exposed publicly into our host infrastructure. Here on Docker Desktop, that means localhost. So let's go to localhost : that 32,000 port, and we get to our Nginx server. Perfect. Now we're doing exactly that, where we're routing through from our service in on this node port out to the target port that the pod is configured to listen on. And that's how we get our traffic from our user in through to our container. Now that's where ingress is really helpful because we can match the DNS name to the service port. But in this case, because we're not using ingress, we'll just come in through this node port. Did that answer your question about what is this node port?
Yes, thank you.
Great.
So can I just confirm something? Node ports is usually something that we can use while developing, and if we're not actually using an ingress type of router, or do we use it in production for anything?
Would I use a node port in production, or would I only use it in development?
Yeah.
In most cases, I would not use a node port in production because I know it's going to be exposed publicly. Now, the downside is that in AWS, they don't route cluster IPs, they only route node ports. So in AWS, you have to specify node port. Node port isn't bad though, as long as you have a load firewall around your cluster that says high ports aren't allowed in. And so if you want to route traffic more easily through your cluster, maybe you'll use a node port instead.
I think having some sort of image where I would see how the traffic flows at each hop will help to clear this, because I think between the node port and the service port and the port and the target port, it's a lot of ports, and it gets confusing what hops you're taking. I think port and node port, I get it. It's more the node port and the service port and the ingress, when it all enters the equation, that gets confusing.
I agree. It is confusing. And part of what makes that worse is it's like, I just want to run on port 80. Just let me specify 80 in all of the things. So you'll notice in this case, I said 80 and 80 and 80 and 80. And I just said, I don't care. Just make them all 80. Because yeah, there is a lot going on with all of the ports.
Yeah, but I'm okay in having 4 ports and 4 different numbers, as long as I understand the hops and how you get to it. It's just that from the picture that you had, it was not perfectly clear what the hops were, and it gets a bit confusing, at least in my opinion.
That makes sense. How can we make this picture better?
Yeah, that one. So user gets to, let's say, if you're not using ingress, right? So the user gets through the node port, right?
Right.
And then its traffic, is it forward to this service port, which then reaches out to one of the specific target ports of a container? Is that how it goes?
Yes, the service's job is to take traffic in on both the port and the node port and send it back out on the target port. Okay. The pod that then listens on the container port, and any traffic flowing into that container port gets routed into that container.
Okay, so I get it. So the service is listening on both port and node port. The difference is that node port is exposed publicly, while port is only exposed to other services and ingress. Is that it?
Exactly. The port is exposed publicly outside the cluster, or the node port is exposed publicly outside the cluster, and the port is only exposed internally to other ingress, maybe other services, maybe pods. The cool part is that this service name becomes a DNS name inside of our cluster. Okay. So in this case, our service name is nginx-service. So if we had some pod that did say curl HTTP nginx-service on port 80, then it would be able to get at our service and be able to route traffic into these pods. That DNS name happens automatically based on this service name.
Okay, so for an ingress, because the ingress is an internal cluster component, so the ingress can hit the service on either port or node port, it doesn't matter. But in the case of AWS, the type of ingress, is it the ingress or is it the service that you are forced to use the node port? I didn't get that part.
Right. In AWS, the load balancer, the application load balancer that they create to be able to make these services work, actually will only route node port traffic. It doesn't route port traffic.
Okay, but that application
I find that to be an incompatible implementation on AWS's part. I just think that's really silly.
but that application load balancer, is that the service or is that the ingress? That's the service, right? Or is it?
That's the service, yes.
That's the service. So it's the AWS implementation of the service load balancer that is only able to receive is only able to receive traffic on node port.
That is correct.
but it does receive traffic on port from inside the cluster, right?
I haven't been able to get it to route to port. I've only been able to get it to route to node port.
And when you say to route to, you mean from the outside, not from the inside.
From ingress to the service.
From ingress. Okay, so for some reason,
Yeah.
only if the traffic comes from ingress to the service. But isn't the ingress cluster internal component? So that
Yes, ingress is internal. So why is it only routing node port internally through the cluster and not actually also routing port? I find that to be weird.
Okay, it's okay.
Yeah.
I kind of get it now.
Ingress is about mapping host names to services. And so the ingress will map example.com into this service named this particular service name.
It's just going to be like a reverse proxy or something, right?
Exactly. Ingress is a reverse proxy based on this host name. Service is a reverse proxy around all of the pods based on its service name. So why do we have two reverse proxies in front of this thing? Yeah, Kubernetes is weird.
But I guess you can have multiple services, but you're only going to have one ingress into your cluster, right?
Right. I'll probably have one ingress that specifies my public host address, but inside that ingress, I might say, and this URL goes to this service, and this URL goes to this service. For all of my microservices within my cluster, I'll have one service and one deployment that will specify that DNS name, so that as my containers are reaching out to other microservices within the cluster, they will reach out to a different service name to reach those other containers.
Okay, thank you.
Yeah. The services are weird. Okay, let's talk about mapping because we skipped over that earlier. Here's this selector section inside my service. Now this selector section says I'm looking for pods that say app nginx in them. So if we look at our deployment definition, our deployment very specifically says, oh, actually, before I do this, let me delete this before I try to deploy it and it doesn't work. The selector says, I am going to route to all pods that say app nginx. Here in our pod template section of our deployment, we said that all of our pods have this label. Now we could also say version is v0.1, and all it needs to find is all the pods that have this label. So it'll still route to all those pods. Now we could say, I want you to route to company myco. And so now it wouldn't route to any, but if we added that additional label here, now it's going to route to all of the pods that match that particular selector. So here inside of our service, we'll specify the selector, and inside of our pod definition, either as a pod or as a template inside of our deployment, we will specify those labels so that service knows which pods to load balance over. Now that's really cool. As long as we have those matching labels, then we'll be able to load balance across all of those pods. The cool part is that these pods don't need to exist when the service is created. When it tries to route a request, it will go discover all those pods and round robin across them. So if the pods are coming up and coming down, when another request comes in, it will route to one of those live pods. Now, inside the deployment, we also specified match labels. This is an optional section, but we chose to define it in this case to say this deployment is responsible for all of these containers, all of these pods. So we added some extra content. So let's add that here. And now our deployment says, these are the pods that I've created. These are the pods that I'll manage. Now, if we don't have this selector section inside of our deployment, then the deployment will just keep track of the pods that it launches, and that works out really well as well. So we did the demos of the YAML configuration files as we went. But one of the things that always trips me up is I'm here inside my pod definition. Let's do the resources thing. Now I have this dash here. Why don't I have a dash here? Well, YAML is a superset of JSON. So let's take a look at what this object might be if it was a JSON object. So here I will switch this to JSON. And now we have an API version of v1, and we have a kind of pod, and we have a metadata section that itself is an object, and we have a spec section that it is also an object. Inside that, we have a containers section, and that is an array. And now we have various elements inside this array that are objects. Now, the first object that we have, that's what this one specifies, is an object that says name is Nginx and image is Nginx Alpine, and ports itself is also an array. So here we have container. Nope, that's an object actually. Oh, I've got my curly braces all over the place. There we go. Container port is 80. And we could fill out the metadata section. I'm going to skip it for now, though. But this is the object that is inside this array. So container specifies that it is an array. Here's an object inside that array. So if we had a second container in this list, it would look like that, and we'd have another dash here. So why don't we have a dash here? Because this is the entire object that is that element in this array. Yeah, YAML is cool.
Hey,
but this
Rob,
YAML to JSON is kind of an interesting way to be able to discover those details.
Yeah, but I do think that ports
Just-
is an array, no?
yeah, exactly. That's what I was
Oh
going to
yes,
ask.
ports is an array, and it has a object inside of it.
Yeah. And it's just a pity that the Kubernetes ecosystem has not decided to use JSON instead, and then we wouldn't have this mess.
Yeah. So Kubernetes, a lot of Kubernetes is stumbling over YAML files. And so hopefully we've demystified them a little bit with that map of ingress to service to pod. But we're gonna dig into, and so DNS, when a pod reaches out to another service, so I'm gonna say backend :3000, then I'm gonna reach out to this backend service on port 3000 that will then route that into the backend pods. I love that services become that DNS name. The Kubernetes CLI, here's some good reference material for as you're digging into it. We demoed a few of these as we got through the process. And so here's our next task. And this will probably carry us the balance of the duration, but I'll come back in an hour so that we can dig through interesting things. We just did Welcome to Kubernetes. Our next job, 6, 7, and 8, will get us to the point where we can spin up content inside of Kubernetes. We're going to use the same containers that we built in 2, 3, and 4, and we're going to now deploy them as content inside Kubernetes. Any questions before we dig into 6, 7, and 8?
In terms of timing, when do you expect the whole workshop to finish? Just for my reference.
I can't hear very well. Can you say that again?
Yeah, in terms of time, when do you expect the whole workshop to finish?
I believe that we're done at 5 o'clock. Is that right?
That's in 15 minutes.
That's in 15 minutes?
Yeah.
Then I think I'm wrong. Oh, yes, we are done in 15 minutes. I talked too long. Apologies.
No, it's okay.
So if we were to come back in an hour, we would be done.
Yes, that's what I was trying to understand. What would be our schedule, considering there's still 13 to 20 or something?
Yes, so it sounds like the rest of this may be take-home homework. Apologies.
Yeah, that's what I thought would happen. Okay. Not a problem. But anyway, I think it was interesting that you responded to a lot of our questions, and that was great.
Yeah. Well, then let's dig into the part that I was going to do as we cleaned up. One of the things that we did today was we created a lot of Kubernetes and Docker content. So maybe our drive is kind of full of stuff. Let's talk about ways that we can now go optimize that and clean it up. kubectl get all. I now have a bunch of content running inside of Kubernetes that I need to remove. Now I could say kubectl delete a particular thing. So in this case, I'll say delete this service, and that will remove the content from here. I can also say kubectl delete deployment, kubectl delete service. Oh, I didn't do the -f. -f. So in the same way that we said kubectl apply, we can say kubectl delete. kubectl get all. What do I have left? The other way that we can do this, and I'm going to back up one folder so that we can see the entire start folder there. I can say kubectl delete, and I can pass it a folder. And so it's going to now iterate through all of the content in my folder, deleting each piece. Now, in this case, it says, hey, I've already done that. So, yep, there's nothing there. kubectl get all. And now we see we have no content running inside of our Kubernetes cluster. Let's flip back over to the Docker side. Docker container list. And I'm going to pass in the -all so that we see both running and exited containers. Now I'm going to say Docker container stop. Now in this case, it's already stopped, so this will happily do nothing. But that stops the container, Docker container rm. That one, and now it will remove it. Now, if I have a whole lot of containers that are exited, but not cleaned out, then I can say Docker container prune, and that will remove all of the containers that are currently running, or that are currently stopped. So I'm going to say yes. It won't stop running containers, but it will remove all of the stopped containers. So it looks like I had quite a few. Docker container list. I see that now I don't have any running containers. Now that's a little bit deceptive because if I come in here into my settings, then I will see that Docker desktop is hiding the Kubernetes control plane from me. So I could choose to show those Kubernetes control plane containers. In this case, I've chosen not to. And so that's why I was able to delete a whole bunch of containers, even though I didn't have any running. Let's do the same thing for Docker volumes, Docker volume list. In this case, it looks like I don't have any volumes. Docker network list. Do I have any extraneous networks? Nope. Docker image list. And here's where you might see a lot of interesting things. Now I have this hello node image, but I also have this none image. Yeah, I created a duplicate label, and so it unlabeled this old one. I can do a similar one. Let's do a Docker image rm, this hello node v 0.1, and that will remove that image. It won't remove it if it's in use, by the way. And then I can do a similar prune, Docker image prune, And I'm going to say -F, which automatically says yes. And that will remove any of these untagged images. So now I will do a Docker image list. And I have a much smaller list here in place. Now that's perfect. These are the base images that I downloaded, so I'm not going to delete these, including a bunch of images specific to my Kubernetes control plane. I can do all of these things together by saying Docker system prune, and that will prune all of the things except for in more modern versions of Docker, it doesn't actually prune volumes. So I'm going to say --volumes, and now it will prune unused volumes too. Now that's helpful. If I am storing credentials or I am storing data inside of volumes, I don't want to delete the volumes by default. So that's a good way to start to remove content. So now I've deleted all of the content that we built today. That's cool. Now WSL will start to reclaim that space and hand that back to my Windows operating system. Perfect. So if you found a lot of places where you have extra content kicking around that you want to delete, then this is that mechanism for being able to prune it. Any questions on deleting content? The other piece is this Kubernetes and Docker best practices. And we don't have time to go through all of them, but I really would point you to this. I'll highlight a few of them as we go through. One process per container. The cool part here is that Docker and Kubernetes will monitor that process. And if that process dies, then the container is unhealthy and the container will probably exit too. Similarly, one container per pod. If the container is unhealthy, the pod will be marked as unhealthy, and Kubernetes can say, hey, I'm supposed to have 3 of these running. That one isn't healthy. I'm going to terminate that, and I'm going to spin up a new one, maybe on new hardware, or just restart it as it is. So a good rule of thumb, one process per container, one container per pod. If you have the need to run more than one process, run them in different pods. That's perfect. All else being equal, you probably want to rebuild and redeploy your production images frequently. There is no Windows update inside of containers. These are meant to be short-lived things that will get recreated and restarted frequently. So I like to give my ops team the ability to push production builds whenever they find the need. If a pod is unhealthy, push rebuild and recreate the container. I'll probably also do it on a cron. So maybe run once a week or every night. I will rebuild the images to get the latest bug fixes and patches from the upstream dependencies. Now that does mean that I need to have good unit and integration tests to validate that I haven't broken anything in that process. But all else being equal, that's the way I patch. I rebuild and redeploy. We didn't have time to get into secrets, but store secrets carefully. You don't want to get secrets to end up in your source control. And that goes double for Docker files and Kubernetes YAML files. Keep those secrets in an external configuration store whenever possible. The Kubernetes dashboard is wonderfully helpful, but also really dangerous. I've got the Kubernetes dashboard right here, and it's a great way to be able to kind of visualize your cluster. But there's also this create button. If you have access to this Kubernetes dashboard, you can create new resources in your cluster. By default, this dashboard is only exposed as a cluster IP in your cluster, but put an ingress in front of it or switch it over to node port, and it's now exposed publicly. And authentication is not on by default. So it's really easy to accidentally expose this dashboard to places where people might be able to spin up new content in your cluster without your permission. All else being equal, I would invite you to delete the Kubernetes dashboard, use the kubectl command line instead, and take these metrics, push them through Prometheus to Grafana, or push them to an external Splunk or Elk cluster, where you can start to manage this content offline in a place where you can't alter your cluster. Version control your YAML files. We created a bunch of Docker files, Docker Compose files, Kubernetes YAML files. All else being equal, put those together with your application in the same repository. Now, if ever you need to rebuild a previous version, you can go to exactly the YAML files that you had at that particular version. And when the automated build is doing all the things, it knows exactly what version of our resources we need. If, for example, we need to make adjustments to our Docker files or our Kubernetes YAML files, we can do that in our feature branch. And as our feature branch gets merged into develop and then ultimately pushed into main and deployed, we have those changes enumerated alongside of our application. That's really helpful. We played a little bit with caching layers, and we didn't talk about this a lot today, but it's really helpful to be able to play with those caching layers to be able to ensure your builds can rebuild quickly. Gratuitously add labels. This is a really good one. We had a few labels inside of our pods. We did a company, we did a project. I really like to put my Git hash as a label in here. So I'm going to pop open my deployment again. And here in our deployment, we will take a look at these labels. Now, I'll probably just leave that. Actually, I usually remove this section completely, but I will have Git hash, and I'll let my build system add this detail into place. Now that's beautiful. When I do a kubectl describe, kubectl describe pod nginx, which right now will not work because it's not running, then I will get the exact Git hash that I use to be able to build this content. Oh, that's perfect. Now I can say git check out that Git hash, and I'm working with the exact code base that produced that build. Now I can really easily reproduce that version. Adding gratuitous labels really helps you to make that connection between the content that you've deployed and the source code that you need, or maybe describing the product that you have, the department that's responsible for this. You may choose to, in time, create policies where every content inside of Kubernetes has to have labels that identify the project and the team associated with it. It's been really fun getting to show you Kubernetes, and I invite you to dig into this Kubernetes hands-on workshop. And we got through the Docker section, the Kubernetes section was next, and here is the process of installing this content on a cloud, which I hope you'll find incredibly easy as you get there. Any questions about Kubernetes? Any thoughts that you have that we want to explore before we sign off?
One thing that would be interesting for me, but I don't know if you have time or if there's anything you can say in just 1 minute or so, which is regarding multiple environments like dev, staging, and prod. And whenever I'm looking and researching for info, it's easy to find the configuration files that mimic your dev setup, but sometimes it's harder to understand how to manage all these environments at once.
Ooh, good question. Dev and test environments. We didn't talk about namespaces within Kubernetes, but let me show you this. There's a couple of ways to solve this. kubectl get namespaces. All of the Kubernetes content is inside the kube system namespace. And that's why when we did a kubectl get all, we didn't see the Kubernetes cluster. But if we did a kubectl get all -- namespace kube system, we can see all of the content running the Kubernetes cluster. So how might we do dev test with this knowledge? Well, one way that we could do it is we could create a develop namespace and a production namespace and be able to keep those separate. Now, that works for a while. There are some resources that are cluster-wide, and so that may not be a perfect solution. A different way to go is to have a cluster that is for development and a cluster, a production cluster rather, and a non-production cluster. Now, in our non-production cluster, we might have different namespaces for different developers or different teams. And in production, then we only have production running content. So now how do I manage that? kubectl config get contexts. Now here are the various contexts that I have running inside my, that I have configured in my environment. I have one for Docker Desktop. When minikube is running, it will add another one. And then I have one for my production cluster running here on Azure. So I can say kubectl config use context Docker Desktop. And now I've switched over to that cluster. So perhaps we have a production cluster that is named one thing, and we have a dev test cluster that is named something else. And then developers are also encouraged to use Docker Desktop on their local machines, or maybe minikube or K3s, and they can run local content that way. Switch between your various contexts, and now you can connect to the cluster that you need to accomplish the task that you need. In time, you may find that most people shouldn't have production access, and so they shouldn't include a config to the production cluster. Does that help answer that question?
Yes, partially at least. So if I understood correctly, I can, each context is its own Kubernetes cluster. So by having multiple contexts, I can have multiple clusters, one for each environment. What I still am not sure is how to best manage the configuration files for all those contexts. And as you said, if you don't want to give a production context access to developers, how do you manage its configuration files? Because you do want to version control it and all of that. So how to manage all of this? I'm still not sure what the best practices are.
Yes. So how did I authenticate to these? In this case, I actually used AZ login to be able to get into Azure. And then I said AZ AKS get credentials. And that gave me the credentials that I needed to be able to log into this cluster here. So it doesn't just appear just because I've noticed this cluster, but I actually have to log into that cluster to be able to get access to it. How would we manage all of these clusters? Well, all of the configuration details about how to start Kubernetes is in similar YAML files. And so we could version the cluster configuration if we wanted to in a different repository. Now, we might not expose that to developers. Maybe we have our Kubernetes configuration repository and specify that differently from the deployment details. Now, one of the things that we might want to dig in here is I might have a connection string to a particular database. Now, I don't want that connection string baked into my container. I want to be able to inject that as an environment variable. So I'm going to say environment, and I'm going to say that connection string equals server foo. YAML is fighting me. Nope. I always have to go look up the syntax because it's ever so slightly different between Docker Compose and Kubernetes. There we go. Connection string is server foo, database bar, user baz, pass, foo bar. And so now we have our connection. Is it not environment? There we go. Oh, and this, nah, I think it is that way, but it's going to be squiggly.
Okay.
Now, this is that environment variable that I need to be able to configure my container so that the container will go in the right place. Now, here's a secret that is currently in this YAML file. Now, in time, I probably want to take this out and I want to put it into a different thing, Kubernetes Secret. And so I can put it inside the secret document, and this secret YAML file, here's an example of a secret. This one happens to be base 64 encoded, which is pretty cool. I will take this secret and I will have a secret per environment that is maybe already applied to my cluster. And then I will link this secret into my pod. So I can say, instead of env, I will say env from secret, my secret. I don't have that syntax quite right, but now I've specified that my secrets aren't here in my pod definition. They're over there in that secret file. So now I'll have a secret per cluster, one production one dev test one local one, maybe one for the pre-prod server, one for the development server, one for team A, one for team B, and I will put those in different secrets. So now in this global file, I don't need to specify the specifics for each cluster.
But shouldn't, what do I do with those secret YAML files? Can I not commit them to my version control repository? Am I not exposing the secrets publicly to everyone if I do that?
Yes.
I trust environment variables. I don't trust configuration files with secrets. So that's something that it's also confusing to me. So if my deployments are all the same, it's only some URLs and config variables that change by using the environment, I can understand how I would do that. But these secret YAML files, I need to push them to under version control. So what do you do?
Yeah, at that point, I would create a very secret private repository. I would commit those YAML files into that very closed private repository, and that's how I would version the secret files. But I'm with you. I really don't like having those secrets in the YAML files even committed at all. And so that's where I might reach for something like Azure Key Vault or HashiCorp Vault and make my application go reach into that store to be able to get its details instead of having them configured this way.
Yeah, because I think even if it's a very private repository, where do you store it? If you're going to store it only on your machine, that's a risk. If you're going to store it on some provider, then you're exposing that secret to whoever is providing you the repository. So I really don't see how this is a good option.
I agree.
I was curious as to what are people using? What's the best practice that everybody uses? Is it those vaults that you mentioned?
Yeah, and this storing secrets is that discussion where I go into a lot of depth there, but unfortunately we didn't have time to get to that one. But yeah, the cool part about this presentation is that it digs into exactly that, where we have various mechanisms where we can store config files, but we must choose to trust various types of people, various systems within our organization before we choose to put our config there.
Yeah. Okay. Okay. Thank you.
Yeah. You've got great questions and it's so much fun to dig in, but it looks like our time has elapsed. Any other questions before we sign off? If you find thoughts in the coming days or weeks, hit me up on Twitter at Rob_Rich, or you can click contact us, contact me by sending me an email or creating a pull request or a comment on this repository. This has been a lot of fun getting to show you Kubernetes. Thanks for joining us here at the Porto conference.
Thank you very much.
Thank you.
Thanks, Rob.